Welcome dear students, welcome back to physics class. Now we are in the lesson electromagnetic induction. In last class we had discussed about the magnetic flux and how the magnetic flux is related to the area, because flux is nothing but field into area, but both also vector quantity, but it is a dot product. So the magnetic flux is a scalar quantity and the SI unit of magnetic flux is Weber. And then we had discussed about electromagnetic induction. That is by simple experiments done by Michael Faraday and Henry. So three experiments we have discussed. In that first experiment, the magnet is moving inwards the coil, or the coil is moving inwards the magnet. So whenever the relative motion between the magnet and coil, an EMF is induced in a circuit. So how the EMF is induced? And this induced EMF is called the induced current, and the phenomena is electromagnetic induction. Okay, right? And next one, there is a long insulating frame. Two coils are kept very closer to the insulating frame. First coil is connected to the battery, second coil is connected to the galvanometer. While you are plugging the key, you can notice that the galvanometer shows a momentary deflections. But in this case, there is no relative motions. But the deflection won't be last long, only at the time of pressing the key, which means this first coil acts as an electromagnet. So that magnetic flux linked with the second coil, the second coil galvanometer shows the deflection. In a third case, we are not replaced, just we did some simple modification. By placing the two coil, the first coil is connected to the battery with the tap key, and the second coil is directly connected to the galvanometer. While you are pressing the tap key, at the second the galvanometer shows deflection to left side. If you keep on pressing, immediately the galvanometer comes to zero. By taking out your fingers, then the galvanometer goes to opposite direction deflection, again coming to zero. So by continuous pressing the tap key, the galvanometer shows the either side deflection. So in this case, we are varying the magnetic field by pressing and releasing the key. Okay. So from all these three experiments, we can come to the conclusion that whenever the magnetic flux linked with the coil changes, from the coil, it experiences induced EMF. Okay, this induced EMF drawn outwards from the coil in the form of induced current, and the phenomena is called electromagnetic induction. Now we are going to discuss about Faraday's electromotive force and the Faraday's law. Now we are going to discuss about Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction, EMI. From the first law, from Michael Faraday, the first law, this already we know. What is the first law? Whenever the magnetic flux linked with the coil changes, an EMF is induced. Okay. So when this is a bar magnet, the bar magnet has the magnetic field. So due to this magnetic field linked with the coil changes, an EMF is induced. This induced EMF draws out in the form of induced current, which are responsible for the deflection of galvanometer. Okay, so the relative motion between the magnet and the coil, an EMF is induced. This is the first law. So the first law is, whenever the magnetic flux is linked with the coil, an EMF is induced. Okay, an EMF is induced. This induced EMF is called induced current, and the phenomena is called electromagnetic induction. So the relative motion between the magnet and coil, which are responsible for induced EMF. So also we can say that the relative motion is responsible for what? The relative motion is responsible for induced EMF. Okay. Moreover, because of the induced EMF only, the galvanometer shows the deflection. Suppose if you stop moving the magnet, the galvanometer won't show any deflections. So the deflection in the galvanometer is lost for a long by the continuous movement of the magnet inside the coil. So the first law states about the induced EMF. So according to the Faraday's first law of electromagnetic induction, whenever the magnetic flux linked with the coil changes by moving inwards and taking outwards. Okay, that is the relative motion between the magnet and coil. So the magnetic flux linked with the coil changes and EMF is induced, and this induced EMF is called induced current, and the phenomena is called electromagnetic induction. So we can state that the relative motion between the coil and magnet is responsible for the induced magnet. Okay, the relative motion between the coil and magnet is responsible for the induced EMF. Suppose if you stop moving the magnet, which means the magnet is held stationary, or the coil and magnet both are held stationary, there is no induced EMF. Okay. Then the second law of Faraday's electromagnetic induction. Okay. So the induced EMF is produced. So the induced EMF. So the produced induced EMF is directly proportional to, what is the induced? I keep on saying EMF. EMF is nothing but electromotive force. Okay, electromotive force between the magnet and the coil, because the coil contains the free electrons. So the free electrons are motivated externally by the movement of magnet into the coil. Okay, so the produced induced EMF is directly proportional to rate of change of flux. Rate of change of magnetic flux. Because while introducing the magnet inside the coil, initially the flux is phi1. Okay, and after some time the flux changed to phi2. So the flux changing, it takes some time. So the rate of change of flux is called the rate of change of flux is directly proportional to induced EMF. So here we can say that the induced EMF is directly proportional to rate of change of flux. You may ask the question, why sir you are mentioning phi2 minus phi1? Because the flux difference. So we can use to say the flux difference. So the flux difference, initial flux is at t is equal to 0. After some time, when t seconds, the flux is phi2. So flux difference by time. Within a certain time interval, how much the flux changes from the pole to the coil, which is responsible for the induced EMF. Okay. And the proportion become equal. We have the constant k into phi2 minus phi1 divided by t. But the value of k is taken as 1. Therefore, E is equal to phi2 minus phi1 by t. Okay. The induced EMF is equal to phi2 minus phi1 by t. Why we take the value k, that we will be learning in higher classes. Okay. Suppose if d pi is a small flux, d pi is a small magnetic flux, and this magnetic flux, that is a small change in magnetic flux. D pi is a small change in magnetic flux, and dt is a small time interval. Then how can we define this induced EMF? Then the induced EMF in the circuit is, then the induced EMF is denoted, as E is equal to minus d by dt. Here the negative sign means, what is the negative sign? Negative sign, it means the induced EMF is always opposes any change in flux linked with the coil changes. Any change in flux linked with the coil changes. Okay, linked with the coil or the circuit. Okay, suppose we used not a single turn, many turns in the coil. If the coil have a n number of turns, then what is the induced EMF? If the coil has n turns, then the induced EMF is minus n into d pi by dt. So this is a formula for the induced EMF. Okay, we obtain the induced EMF by increasing the turns, that increase the induced EMF. So induced EMF is proportional to n. By increasing the number of turns, that increases the induced EMF. So these are the two laws given by Michael Faraday about the electromagnetic induction. I repeat once again, Michael Faraday gave the two famous laws about the electromagnetic induction. The first law that gives the definitions. Let us take the copper coil or any conducting coil. The external terminal of the conducting coil is connected to galvanometer. Now you choose any one of the pole of the magnet. Now I am introducing the north pole of the bar magnet near the coil. In generally, around the bar magnet in a certain area, how many field lines are crossing, that indicates a flux. So the initial flux is phi1 when time is 0. By moving the magnet, the flux changes. So the flux difference is from phi1 to phi2. So the difference is phi2 minus phi1. So the flux difference changing, it takes some time. So the magnetic flux linked with the coil changes and EMF is induced. So this induced EMF, which is drawn in the form of induced current outwards, due to the induced current, the galvanometer shows a deflection. Okay. And if you continue moving the magnet inside the coil, the galvanometer also shows a continuous deflection. Suppose if you stop moving the magnet inside the coil, the galvanometer also won't show any deflection. Here, when a north pole is introduced, the deflection is to right side. While taken out the north pole outside, which means the south pole is approaching, the deflection is opposite side. Suppose if the magnet is kept inside the coil, the galvanometer won't show any deflection. So introducing the north pole, deflection to right side. Taking out the north pole, deflection to opposite side. By the continuous movement of magnet inside the coil, the galvanometer shows deflection. So the relative motion which is responsible for, that is the relative motion between the conductor and coil, is responsible for the induced EMF. And from second law, the induced EMF produced in the circuit, which is directly proportional to rate of change of magnetic flux. So the rate means with respect to time. Change in magnetic flux is phi2 minus phi1. And whenever the proportion become equal, we have a constant, but this constant value is taken as 1. Okay. Then E is equal to phi2 minus phi1 by t. Now we'll assume d pi is a small change in magnetic flux. Okay, difference in the flux. Okay, so the difference in the flux is very small amount, and dd is the small time interval. So within a small time interval, d pi is a small change in the magnetic flux. Then EMF induced in the coil due to the relative motion, which is equal to minus d pi by dt. We didn't use negative signs here, but here we brought negative signs. What does the negative sign mean? While introducing the north pole, it opposes the change. Okay, so the repulsive force is greater. So the induced EMF is always opposes any change in the flux linked with the coil, or this we can say this as a circuit. Okay, so if the coil have n number of turns, okay, the copper coil have a more number of turns, then all the turns are added, then the induced EMF is equal to minus n into d pi by dt, which means increasing the number of turns, that increase the induced EMF. Okay, next we are moving to the Lenz law. Okay, in the previous topic, Faraday's law of electromagnetic inductions, we have seen the two laws. In the second law, the induced EMF, which is equal to minus of small change in flux divided by small time interval. The negative sign that represents what? From Lenz law. So we are going to know why we use the negative signs. So that can be verified from Lenz law. This lens is not like a transparent light medium, that is LENS. This is Z. Okay, this is another one, scientist. Okay, according to this Lenz law, the direction of induced current is such that it opposes the change in magnetic flux. Okay, the direction of the induced current or induced EMF in such that it opposes the change in magnetic flux, is responsible for its production. Suppose we have a coil. This is a circular coil. And in the circular coil, we introduce the bar magnet. Here, the north pole of the magnet is introduced. This is north, this is south pole. Okay. Here, the north pole of the magnet is introduced inside the coil. And generally, the field lines around the bar magnet is from north to south. The field lines externally from north to south. So this is the direction of field line. So the magnetic flux linked with the coil changes, which means when a north pole is approaching, so the approaching north pole of magnet, bar magnet with the coil, what happens? In a coil, the EMF is induced. This induced EMF is just opposite to the direction of the magnet. So the direction of the induced EMF is a field length that opposes. So this is the direction of induced EMF. So this is like south, and this side become north. So this is the direction of induced EMF. Okay. So the resultant, it will be in a anti-clockwise direction, and this phase with respect to the observer. So magnet yaar move பண்றாங்களோ அந்த observer க்கு இந்த coil ஓட இந்த phase என்ன polarity ஆ இருக்கும்னா it is like a north polarity. This is north polarity. So to the observer, this side is like a north polarity. So here this indicates the induced EMF. So this indicates the induced EMF or induced current, and these are the magnetic field lengths from induced current. These are the magnetic field from induced current. So here the flux is increasing. So the flux in this region is increasing. By increasing the flux, the induced current that opposes. So the induced current that opposes the increasing flux and the north pole of the bar magnet is introduced. So the direction of the induced current is anti-clockwise. Look at that. What is the direction? The direction of the induced current is anti-clockwise. So the magnetic dipole moment in this case, it become a north pole. The magnetic dipole moment in this case, the magnetic moment that is M vector is north polarity. Here it becomes a north polarity. Moreover, this induced EMF that opposes the increasing flux. Also, the induced EMF that opposes what? Increasing flux. Increasing magnetic flux. So there is a repulsive force that increasing that is in the increasing flux. Therefore, the repulsive force that increasing the flux. Okay. So, careful Goni, when a north pole of the bar magnet is introduced inside the coil, okay, in the coil, the direction of induced current is an anti-clockwise, because the north pole of the bar magnet, while it linked with the coils, the increasing the flux, that is a change in flux, which increases the flux in the magnet, around the magnet. So, the phase of the coil towards observer become north polarity, and the direction is in anti-clockwise. Okay, and the current flows, induced EMF that flows in an anti-clockwise direction. Same like if you take out the north pole outside, then it becomes south polarity. So how it will be? Listen. We have a copper coil. Okay, this is copper coil, and this is a bar magnet, but we are not introducing, it is not approaching, its receipts are taken away. The north pole of the bar magnet is taken away. When the north pole of the bar magnet is taken away, there is no change in the flux, it remains same. So this is the direction of the field lines around this magnet, but one small change is here. In this case, the induced EMF is in clockwise directions. So what is the direction of the induced EMF here? So this side acts as a north pole and another one side acts as a south pole. So this is the direction of the induced EMF, which is in the clockwise direction. So here, this is the direction of induced EMF or magnetic field lines, and this is also the induced EMF. This is also the induced EMF. Okay. So this is the direction of induced EMF. Induced EMF or induced, due to the induced EMF, we will get the induced current outside, and these are the magnetic field lines. Magnetic field from induced current. This is the magnetic field from the induced current. So when a north pole is first case, north pole is approaching, here the north pole is receding away. The north pole is receding away or taken away. The north pole is receding or north pole is taken away. So when the north pole is taken away, in this region flux is reducing, so there will be attractive force. Okay, so to compensate the decreasing in flux, there is an attractive force takes place. But here the force is repulsive, but here the force is attractive. And due to increasing flux, the induced EMF that opposes, but here attracting. So the direction of the induced current will be in the clockwise. So this phase becomes south polarity. So this phase becomes south polarity. So this phase becomes south. This is like a south polarity, and it will be in the clockwise direction. Okay. So it's a very simple thing. In which case the upper face of the coil towards an observer becomes south polarity means when the bar magnetic north pole is taken away or south pole is introduced. அப்போ ஒரு விஷயம் கவனிச்சுக்கோ, மேக்னெட்டோட நார்த் போல் காயில்ல இன்ட்ரோடியூஸ் ஆச்சுன்னா அந்த ஃபேஸ் நார்த் போலாரிட்டினா ஆன்டி கிளாக்வைஸ். சப்போஸ் நார்த் போல் இஸ் டேக்கன் அவே ஆர் சவுத் போல் இஸ் இன்ட்ரோடியூஸ்ட் அப்படின்னா, if south pole is introduced, the corresponding polarity, what is the polarity? Clockwise polarity. The magnet is the induced EMF is induced. Okay. So in this cases, the increasing flux that opposes the increasing flux that opposes the induced current. So induced current that opposes the increasing flux. But here the flux is reducing, so there is an attractive force. So due to the attractive force, here the magnetic dipole moment is in south polarity. The magnetic dipole moment is south polarity, and also due to the induced EMF, there is an attracting force. And one more thing from this I forgot to say. Yes. So here the flux is reducing, so there will be attracting. Due to the attracting, the direction of the induced current is in south polarity. South polarity means what? In clockwise direction. South polarity means it is in the clockwise direction. So Lenz's law is used to identify the direction of the induced EMF which opposes the change in flux. Okay. So when north pole of the magnet is introduced, the face of the coil towards an observer becomes north polarity, and the direction of induced EMF is in anti-clockwise. If the north pole is taken out or the south pole is introduced inside the coil, then the coil magnetic field faces south polarity and the direction is in clockwise. Okay. So this is the Lenz's law, and it's very important So among these two laws, either Faraday's law of electromagnetic induction or the Lenz law, they may ask 1 mark or 2 mark questions. So concentrate carefully. Next one, verification of Lenz law. So we have discussed the Lenz law. So in the Lenz law, the direction of the induced EMF that opposes the that opposes the flux. Okay, if the north pole is approaching, then the phases of the coil towards the observer become north polarity, because due to the repulsive force between the induced EMF and the flux, so flux is increasing and the direction of the polarity is anti-clockwise. Okay, the same in experimental wise, how to verify? It's a very simple experiment. So look at the first experiment. Let us take the coil. This is the copper coil, and the terminal of the copper coil is connected to a galvanometer and a two-way key. This is a two-way key. 1, 2, 3. This is a two-way key, and this two-way key, and this is connected to a cell. A cell that delivers the potential across the coil. Initially, the galvanometer 0 at the center. Now, in this experiment, now connect this open junction key terminal 1 and 2. Not connecting 1 and 2, we are going to connect it from 2 and 3. So this is a two-way key. Here 1, 2, 3 is a two-way key. Number 1 and 2 connect panna mudiyum, illana 2 and 3 connect panna mudiyum. So now we are going to connect the terminals 2 and 3. So while you are connecting the terminal 2 and 3, the currents in the circuit that flows from positive to negative. So the positive side terminal that acts as a north polarity. So by developing the north polarity in the upper phase, the direction is in anti-clockwise. Okay, the direction is in anti-clockwise. So the lower phase that acts as a south polarity. So the galvanometer shows the deflection from 0 to right hand side. Are you clear? So here, due to the current in a circuit, the coil induced the magnetic field. So the direction of the current also verified. So in these cases, the upper phase have north polarity. So the direction is outwards, and here it is inwards. This is the direction of the field line, and the lower phase acts as a south pole. So due to the upper phase have a north polarity, the direction is in anti-clockwise. Okay, so galvanometer deflection to the right side. Suppose if the galvanometer shows deflection to the left side, then the upper phase become a south polarity, that is the clockwise. And another one experiment, the same experiment but one small change we are going to do. Instead of connecting 2 and 3 in the key, remove the key from 2 and 3. Now you make a link between 1 and 2. What will happen? We have the same coil, and this is galvanometer. This is the key 1, 2 and 3, and the terminals are connected to the cell. Now we make a link between 1 and 2. While making the link between 1 and 2, at the time you are introducing the north pole of the bar magnet. While introducing the north pole of the bar magnet, due to the flux change, it opposes the magnetic flux. So the increasing the flux that opposes the induced EMF. So hence the current is induced, and the galvanometer shows the deflection to the which side? Right side. Now you will take the bar magnet outwards. While taking the bar magnet outwards, the deflection found in the galvanometer is opposite directions. So when a north pole is introduced, deflection is right side. When the south pole is approaches or the north pole is taken away, deflection is left side. So by the continuous, inserting right side, taken away left side. Inserting right side, taken away left side. So the relative motion between the magnet and the coil. In the coil, the EMF is induced. Here, the EMF is in anti-clockwise directions. So the relative motion between the magnet and coil an EMF is induced that can be verified by the deflections. Okay. So from the conclusions, the induced current is always opposes the change in magnetic flux which produces it. And also the mechanical work done in moving the magnet with respect to coil that changes into electrical energy. So the mechanical work done of moving magnet into the coil that changes into electrical energy. So the work done against the repulsive force that changed into electrical energy. So the mechanical energy in this relative motion between the magnet and coil that changes to electrical energy. Okay. So this is the experimental verification of Lenz's law. Okay. Thank you.